Hello and welcome to section 3.7, optimization. Now in this section we are talking about finding maximums and minimums of functions. And so we are going to be dealing with, this is kind of like the related rates that you did in the earlier section. So we're going to need to first identify things that we're trying to solve for. Are we trying to solve for a maximum of volume? Are we trying to find a minimum of area? And it just kind of depends on what's given in the problem, and it's just a matter of reading through the problem and figuring that out. And then there's always going to be a primary equation, and the primary equation is the one that we are going to maximize or minimize. And so if it says maximize the area, then you're looking for an area equation that you can take the derivative of and find maximums. And then or same thing with its minimums. If it's saying the minimum volume or the minimum radius you need for this cone or something to make it the volume, then you're going to minimize the volume formula or the radius part of the, so that's what we're dealing with. And then there's always the secondary equation, and the secondary equation in this example is the equation so that you can get this into one variable. So that you're not dealing with implicit differentiation. And so that's going to be the trick to these, is most of these guys, when you're dealing with the primary equation, is going to have two different variables, and you don't want two different variables, maybe three. You want to replace one of the equations or one of the variables for something in the secondary equation so that you can get it all in one variable. Then of course, once you differentiate it, then you'll find the values you're looking for and check out and see if they make sense. So I have an example for us that deals with this, and we'll talk a ton about this in class. We'll practice a bunch of these. But we are going to find a minimum distance. And since this is a minimum distance problem, that means that I got to think of a couple things. One, I need to minimize something. And what am I going to minimize? Well, I'm going to minimize distance. Well, what is distance? The distance, well, when I think back to geometry class, I think of distance formula. And so that's going to be my primary equation, is that I'm going to have to use the distance formula because I want to find either a maximum or minimum distance. So that means that it's x minus x1 squared plus y minus y1 squared. And so that's my distance formula. And so just by reading this, I know what's happening. Now let's do a quick little graph of this. Remember that this is up 4 and an upside down parabola, so something like this. Something like that. And I'm dealing with the point 0, negative 2, or 0, 2, which is this point here. 0, 2. And I want to find the minimum distance to get to a point on my graph. And so that would be an xy. Over here would be the minimum distance. And then over here will be a negative x and a y. So that's really what I'm trying to do for this. And when I try to do this, then I would say, okay, well, I'm going to resketch this. When I'm going to do this, I'm going to go ahead and find that we're going to have to differentiate something. And that's where the primary and secondary equation comes into play, is that, well, my primary equation is distance, so that's what we're going to deal with. And so let's go ahead and deal with it. And so if we are looking at this, I could plug in my given formulas and given points, and that's 0, 2. So that's going to be x minus 0 squared plus y minus 2 squared. And so, yeah, that helps a little bit, but you'll notice that I'm still dealing with two variables. And so what I'm going to do then is I'm going to get x squared, and over here I got y minus 2 squared. So I'm not going to replace I'm going to replace y if this is my primary equation, because I know it's my primary because I want to find minimum distance. So I got to minimize, and I said that means I'm looking for the derivative of the distance formula. But I have two variables. I don't want to do implicit differentiation. What I want to do is I want to find I want to do this in one variable. So you'll notice that up here in this equation, that y equals 4 minus x squared, they told me what y was. So I'm going to replace that y value with the 4 minus x squared. So I've got x squared plus 4 minus x squared minus 2 squared. Well, I can simplify inside that parentheses a little bit more, and now it's just a little bit of algebra here. And so now you'll notice everything's in one variable, which makes life a little bit easier. If I multiply this all out, I end up with underneath my square root x squared plus 4 minus 4x squared plus x to the fourth. And so my final distance formula, all simplified before I differentiate, is x to the fourth minus 3x squared. It's 3x squared plus 4. Now you're probably thinking to yourself at this point, boy man, I have to take the derivative of this thing and it's going to do a chain rule and it's going to get really nasty. This is the one time where you don't have to do that. Because let's think about this. If I have the square root of 16, the square root of 9, and the square root of 4. Okay, looking at these numbers, which one is the biggest? Well, that's square root of 16. Which one's the smallest? That's 4. If I take the square root of each one of these, I get 4, 3, and 2. Well, looking at this, the square root of 16 is 4, and the square root of 4 is 2. So when I have the biggest number underneath the square root, I get the biggest number outside of the square root when I take it. So if I have the smallest number underneath the square root, then I get the smallest number outside the square root. So I can drop this square root and say, well, if I get a big number under here, if I get a big number, that's going to be the biggest number. If I get a small number, that's going to be the smallest number, because the square roots, it doesn't really matter. You still end up with the same proportional size number. So if I'm going to, so basically what I'm telling you is that in this one, because I'm taking the square root of a number that I'm trying to maximize or minimize, then I don't need the square root, which will make life a little bit better for us. So now if I differentiate this with respect to x, I get something that looks like this. So that's supposed to be a 6x squared. And so then my differentiation with respect to x factored could be something like this. And so now, what do we do to maximize or minimize? Well, we set these guys equal to 0. So 2x equals 0, and 2x squared minus 3 equals 0, which means that x is either 0 or x is plus or minus the square root of 3 halves. And so now we need to go ahead and find out what's going on here. And so I'm going to have to do a first derivative test to see what's happening. So well, negative square root of 3 halves at 0, and at the positive square root of 3 halves, I will have values that will tell me what's going on. So my first derivative test, we're going to test whether we're increasing or decreasing around these points. So I'm going to choose something like f prime of, say, negative 2. That's smaller than the square root of 3 halves. And so doing that, putting in negative 2 into the function, well, I'm going to use this guy right here. So negative 2 means this is negative, and negative 2 here means that, let's see, negative 2 positive here, and so I end up with a negative times a positive, which means that's negative, so we are decreasing there. And then between 0 and negative 3 halves, probably would be something like, well, we could try, let's try negative 1. I believe that's between there. But we'll put negative 1 in. Negative 1 means this is negative out here, and negative 1 here would be positive 2, but I'm subtracting 3, so that's negative. So a negative and negative means that we are positive, so we're increasing at negative 1. So then on the other side,